Hi, we're going to talk about another gas law called the ideal gas law. The ideal gas law is PV is equal to nRT. So when I say PV, I mean P times V, and N, R, and T are all multiplied together. So you should recognize everything in here. P, of course, is pressure. V is volume. N is number of moles. And T is temperature. Remember, in gas law problems, you have to do temperature in Kelvin. The one thing that's new that you haven't seen before is this capital R. And capital R stands for something called the universal gas constant. So R is just a constant. It's going to have a certain value and certain units that are going to make all the other numbers and units work out. So knowing that R is a constant, let's isolate R, meaning solve for R. So let's divide both sides by both N and T. And what you'll get is you'll get PV over NT is equal to this gas constant. So this should actually look a lot like one of your two variable gas laws. Well, not the two variable gas law, but the combined gas law. So if we put ones here, P1 times V1 over N1 T1 would be equal to P2 times V2 over N2 T2. So the reason you can say that one side is equal to the other is that is in fact a constant relationship. So that's why you can say that they equal a constant. So I want you to see the relationship between the combined gas law that we have here and then this new gas law, which is an ideal gas law. So the new gas law, you're only looking at a gas at one point in time instead of looking at a gas at one point in time and then changing something and looking at it at a second point in time. So that's a difference between the ideal and the combined or your two variable gas law. This is the universal gas constant, R. So you see three different values with three different units here. And you might say, well, if it's a constant, why are there three different values? And that has to do with the fact that in each case here, you can see you have different pressure units. So don't forget, R is equal to PV over NT. So on the top of your fractional units here, you should have units of volume, which is liters. You should have some pressure units, which in this specific case is atmospheres, but you can see that that changes with the different R values. Your N units are moles, and your temperature units are always going to be in Kelvin. So if you're given degrees Celsius, you have to convert it to Kelvin. Also, if your volume is given in milliliters, you have to convert it to liters in order to use these R values as is. But what I have you do is I have you pick the correct R value depending on what your pressure units are. So if you have millimeters of mercury or torr, they're equivalent. You're going to use the 62.4 value for R. And if you have your pressure units in kilopascals, you'll use the 8.314 value for R. If you have pressure in kilopascals, you could always convert it to atmospheres and then you would only ever use, this value for R. That's kind of up to you. But I'll give you all three of them and then you can kind of decide on your approach. So let's do this problem. Pause the video and actually copy this down, please. What is the volume of 23 grams of neon gas at 1.0 degrees Celsius and 2.0 atmospheres? Make sure you copy down the example problem before we just start doing the work. Assuming you've done that, let's start doing the work. We know we have an ideal gas law problem because we don't see anything happening at one condition and then a second condition. So we know we're going to use PV is equal to nRT. So to write a list of variables, since we know we need each of these, we can actually just write PV RT, and then we can go through and take a look at what numbers kind of match up. So here we have 1.0 degrees Celsius, so we know that that's a temperature. So 1.0 degrees Celsius, we might as well just add 273 to it right away, and we'll get 274.0 Kelvin. Remember that 273 doesn't affect sig fig, so we'll go with the 1 decimal place in our answer. It's not going to matter because that's too many sig figs for what we'll end up with anyway. Another number we see is the 2.0 atmospheres. So atmospheres are units of pressure. So we know our pressure value is 2.0 atm. And it says what is the volume. So we know that that's ultimately what we're trying to find is our V. And then don't forget, even though it's never going to say it in the problem, you always have an R value. So look at your pressure units. Your pressure units are in atmospheres. So you want to pick the R value that goes with atmosphere. So from the previous slide, that was 0.0821, and it has fractional units of liters atmospheres over mole Kelvin. Okay, the issue here is that we're not seeing anything for number of moles. So that's like a temporary question mark at this point. But what we do have here is actually a mass. Grams are not units of moles, but it's units of mass, and grams, luckily, and moles are related. Okay, and this is 23 grams specifically of neon. If you weren't told that it was neon, you would have a little bit more of an issue here. But the good news is that we can use the periodic table and we can get the molar mass of neon, and we can go from the grams that we have, put that over 1, and then do a quick dimensional analysis problem. Grams of neon on the bottom, we can go to moles of neon, and the molar mass is 20.18. I'll just round to 2 decimals there. And every 1 mole of neon, grams cancel, and now we can get to moles. So if you do that math, I'll just take it out to more sig figs than we'll need. So 1.14 moles of neon. And then the great news is that we now have this answer. We know that it's 1.14 moles of the neon. So we truly only have one unknown, which is our volume. Okay, so we will rearrange our Pivnert equation to be V is equal to nRT over P. Okay, so you can stop the video and sub in the numbers and get your answer. Remember units and remember sig figs here. Hopefully you took some time to plug your numbers in, and you should have gotten something on your calculator close to 12.8. So we need to still do sig figs and units here. So the units, you can see atmospheres is on the top here and on the bottom of a fraction here. Moles is on the bottom of a fraction and what amounts to the top of a fraction here, and then same with Kelvin. So then what we're left with is liters, which makes complete sense because we're looking for a volume. And then let's do significant figures. Kind of go back to your beginning. Here you have 2 sig figs. This we didn't really do our number of moles to sig figs. This doesn't matter for sig figs, it's infinite. This had 2, but when we added the 273, now it has 4 sig figs. And then this mass also has 2 sig figs. So it looks like we should go to 2 sig figs. So when we round that and get our final answer, we're going to get the volume is equal to 13 liters. So if you have 23 grams of neon gas at these conditions, it's going to take up 13 liters of space. If you had a different gas, you'd have a different number for your moles here based on the molar mass. So your volume would change even if you still had it at 1 degree Celsius and 2.0 atmospheres. So I wanted to take you through an example that was a little bit more challenging than just being given 3 out of the 4 variables and PV is equal to nRT. So this is combining stuff you already know about molar mass. We're going to take a look at another equation that we haven't seen in a little while. D is equal to m over V. That's density is equal to mass over volume. And what we have in common in both the density equation and the ideal gas law is the volume. So if we solve each of these for volume, then we can set them equal to one another. So density, solve for volume, and remember, people get this wrong a lot. So just put density over 1, and then you can do some cross multiplication. So volume is going to be equal to mass divided by density. And then over here, volume is going to be equal to nRT over P. And now through transitive property, which is my favorite geometric property, by the way, if A equals B and B equals C, then A equals C. Okay, so we'll set M over D equal to nRT over P. Now let's make a goal to isolate density. We'll just have density on one side of the equation. So if I do that math through cross multiplication, I'll get D is equal to mass times pressure over nRT. And then let me just draw your attention to one more thing here. M over N should look pretty familiar to you. Okay, M over N, the units would be grams over moles. Hey, those are the units for molar mass, right? So one other way to write this equation would be density is equal to the molar mass of the gas. So you'd have to know the composition. You can't just say of a gas. You'd have to be told it's neon gas or it's carbon dioxide gas. So molar mass times pressure over nRT. If you know the molar mass, you can find the density. If you know the density of the gas and the certain conditions, you can find the molar mass. Okay, so that's just another way to kind of use the ideal gas law.